Picture yourself standing at the base of a massive cliff, gazing up at layers upon layers of rock stacked like the pages of some ancient, stone-bound book. Each stripe and band tells a story not just of this planet, but of the entire solar system's slow, majestic dance across billions of years. These formations are far more than just geological wonders. They are cosmic archives, holding within them the subtle imprints of shifting planetary orbits, gravitational tugs, and celestial rhythms that have guided the evolution of our corner of the universe. What if I told you that the very ground beneath our feet contains coded messages from the stars, that within these silent stones lie clues to the grand, invisible patterns of planetary drift patterns that have shaped not only Earth's history, but the fate of worlds beyond our own? This is the story we're about to uncover together, from the birth of our solar system in a swirling cloud of gas and dust to the cutting-edge discoveries that are reshaping our understanding of time itself. We will journey deep into the mysteries written in stone. We'll explore how ancient rocks capture the echoes of orbital resonances, the whispers of cosmic collisions, and the quiet, persistent influence of planets like Jupiter and Venus on Earth's geological and climatic story. This isn't just a tale of the past, it's a key to understanding our place in an ever-changing cosmos, a reminder that we are part of something vast, dynamic, and beautifully interconnected. So come with me as we decipher these celestial diaries, piece together clues from igneous, sedimentary, and metamorphic rocks, and follow the trails left by drifting planets across the eons. What you're about to discover will change how you see the world, not as a static stage, but as an active participant in the solar system's unfolding story. This is more than geology, it's cosmic detective work, and by the end of our journey, you'll never look at a mountain, a canyon, or even a simple stone the same way again. To grasp how ancient stones hold the secrets of wandering planets, we need to travel back to the very beginning, to the moment our solar system sparked into existence. Envision a vast, cold, and silent cloud of interstellar gas and dust, a nebula drifting through the galaxy. Then, perhaps nudged by the shockwave from a nearby exploding star, this cloud begins to collapse under its own immense gravity. As it contracts, it spins faster and flattens into a whirling disk with a burgeoning, fiery protostar at its center, our infant sun. This was the protoplanetary disk, the chaotic nursery from which every planet, moon, and asteroid we know would eventually form. Within this spinning maelstrom, microscopic dust grains started to stick together in a process called accretion. Think of it like a cosmic snowball fight happening in slow motion over millions of years. These tiny particles collided and coalesced, growing from pebbles to boulders to mountain-sized bodies known as planetesimals. Through endless collisions and gravitational tug-of-wars, these planetesimals merged, with the largest ones sweeping up material to become the protoplanets. This was not a gentle process. It was a violent, chaotic demolition derby happening on an unimaginable scale, setting the initial orbits and spins of the newborn worlds. This early period was defined by gravitational chaos. The giant planets like Jupiter and Saturn likely migrated from their original birthplaces, their immense gravity shaking up the entire system. Their movements acted like gravitational pinballs, scattering smaller bodies inward toward the sun or outward to the frozen edges of the disk. This period of planetary pinball, known as the Late Heavy Bombardment, saw a rain of asteroids and comets pummeling the inner planets, including a very young Earth. The evidence for this violent infancy isn't just theoretical. It's locked within the oldest rocks we can find, both on Earth and in the meteorites that occasionally fall from the sky. These meteorites are time capsules, pieces of asteroids that have remained largely unchanged since the solar system's formation. By analyzing their chemistry and isotopes, scientists can read the story of those first few million years. They reveal the precise age of the solar system, 4.6 billion years, and contain microscopic grains that are even older, stardust from other stars that died long before our sun was born. This pristine material shows us the initial ingredients and the turbulent conditions that set everything in motion, establishing the gravitational rhythms and orbital patterns that would continue to influence planetary drift for billions of years to come. The stage was set, and the planets were in motion, beginning their eternal dance, a dance whose earliest steps would soon be recorded in the first rocks to solidify on our young world. After the fiery chaos of accretion, our young planet began to cool, its surface transitioning from a global ocean of magma to the first solid skin of rock, Earth's primordial crust. This wasn't the familiar continental crust we know today, but a thin, unstable shell, rich in dark, heavy minerals like those found in basalt. As it solidified from the molten inferno, it did something remarkable. It began trapping within its crystalline structure tiny, chemical fingerprints of the solar system's earliest environment. The very act of formation encoded these rocks with a snapshot of the cosmic conditions at their birth, a memory of the composition of the nebula from which everything formed. This newborn crust did not get to rest peacefully. It was immediately thrust into a celestial shooting gallery, a period of relentless bombardment by asteroids and comets. But these weren't random acts of violence. They were direct consequences of the gravitational dance happening further out in the solar system. As the giant planets, particularly Jupiter and Saturn, migrated and settled into their orbits, their immense gravity acted like a gravitational slingshot, hurling vast swarms of leftover planetesimals inward toward the sun. Earth in its path bore the brunt of this cosmic crossfire. Each impact was catastrophic, often re-melting large portions of the nascent crust and churning the surface into a hellscape of molten rock and vaporized stone. This process continually recycled the earliest rocks, making them incredibly rare today, but for geologists, finding them is like discovering pages from the solar system's first diary. Some of the most profound clues come from tiny, incredibly resilient minerals called zircons. These crystals are geological survivors, tough enough to withstand the heat and pressure of multiple cycles of destruction and rebirth. Found within ancient Australian rocks dating back over 4 billion years, these zircons are the oldest known fragments of the Earth's crust. When scientists analyze them, they find more than just old age. They find a chemical story written in isotopes of elements like oxygen and hafnium. The ratios of these isotopes tell us that water was already present on Earth's surface incredibly early, suggesting that wet asteroids or comets, the very ones scattered by planetary migrations, were delivering water during the bombardment. Furthermore, the presence of certain rare Earth elements and peculiar isotopic signatures in these ancient zircons points to the types of materials that were bombarding the early Earth. The composition of this extraterrestrial debris varied depending on where it originated in the solar nebula. By reading these chemical signatures, scientists can work backwards. A sudden change in the mix of elements found in rocks from a specific time period might indicate a shift in the source of the bombardment. Perhaps Jupiter's migration cleared out one region of the asteroid belt, suddenly making a different type of asteroid more likely to be flung toward Earth. The crust, in effect, became a record of changing traffic patterns in the solar system, patterns dictated by the drifting giants. So, these ancient rocks are far more than just geological relics. They are cosmic seismographs recording the distant gravitational tremors of planetary drift. The composition of Earth's first crust and the alterations it suffered from above provide a direct and tangible link between the geology under our feet and the mechanics of the celestial bodies orbiting our Sun. They hint at a solar system in flux, where the movements of planets millions of miles away directly shaped the formation and evolution of our own world, etching their history into the very bedrock of the planet. But this story of formation and early bombardment was only the opening chapter. The real ongoing chronicle of our planet's relationship with the cosmos is written by a far more dynamic process, one that continuously reshapes the Earth's surface even today: plate tectonics. Think of the Earth's lithosphere not as a single, solid shell, but as a gigantic, fragmented jigsaw puzzle with each tectonic plate constantly on the move. They drift at about the speed your fingernails grow, colliding to birth mighty mountain ranges, pulling apart to create vast ocean basins, and sliding past one another to trigger earthquakes. This grand, slow-motion ballet is the planet's most powerful geological engine, and remarkably, its rhythm is not dictated by Earth alone. The gravitational tug of the Moon and Sun, and even the subtle, rhythmic pulls from other planets, act as conductors for this terrestrial orchestra, leaving a distinct signature in the rocks that form. When two plates diverge or pull apart, magma wells up from the mantle to create new oceanic crust along mid-ocean ridges. As this molten rock cools and solidifies, it acts like a tiny compass, locking in the orientation of Earth's magnetic field at that precise moment in time. The Earth's magnetic poles have reversed countless times throughout history, and this new crust records each reversal as a distinct striped pattern of normal and reversed magnetism parallel to the ridge. By mapping these magnetic stripes on the ocean floor, scientists have not only charted the history of continental drift, but have also detected longer, more subtle patterns within the reversal timeline. Some researchers propose that the frequency of these flips could be influenced by changes in the Earth's rotation or core dynamics, which are in turn subtly modulated by the gravitational influences of other planets over millions of years. The seafloor, therefore, is a vast magnetic tape recorder, and its playback reveals a soundtrack that might have celestial harmonies mixed in. Conversely, when plates converge, the results are even more dramatic for creating a geological record. The incredible forces of continental collision crumple rock layers, thrusting up immense mountain ranges like the Himalayas and the Alps. Within these folded and faulted rocks, the immense pressure creates metamorphic minerals and structures that tell a story of deep time and immense force. But the rate of this mountain building and the subsequent erosion that wears them down may itself be paced by external forces. Variations in tidal stress from the Moon's gravitational pull can exert a small but persistent influence on the stresses within the Earth's crust, potentially affecting the timing and intensity of tectonic activity over vast timescales. Furthermore, the sedimentation in the basins adjacent to these growing mountains captures a rhythmic story. The amount and type of sediment washing down from the peaks are directly controlled by climate, which is itself driven by astronomical cycles. So the very layers of sand and mud that eventually turn into sandstone and shale hold within them an indirect yet powerful record of planetary orbital rhythms. Even volcanic activity, driven by the upwelling of mantle plumes and the subduction of plates, shows patterns that hint at a cosmic connection. The immense tidal forces exerted by the Sun and Moon don't just affect the oceans, they flex the solid Earth itself, a phenomenon known as Earth tides. This constant, gentle squeezing and stretching can slightly influence the timing of volcanic eruptions by modulating the pressure in magma chambers deep underground. On a much grander scale, periods of massive continent-scale volcanism that created features like the Deccan Traps in India appear to cluster at certain times in Earth's history. While the primary cause is internal from mantle processes, some scientists investigate whether the gravitational resonances from other planets could provide a small, periodic nudge or trigger that helps push a volatile system over the edge at regular intervals. The tectonic engine, with its creation of new rocks, its folding of old ones, and its fiery volcanic outbursts, is therefore far more than just an internal geological process. It is the planet's primary mechanism for inscribing a continuous, multi-billion-year diary, and its pages are filled with entries that chronicle not just Earth's own dynamics, but the gentle, persistent influence of its celestial neighbors. While the immense forces of plate tectonics build and destroy the very foundation of our continents, there exists another, quieter geological process that acts as the planet's most meticulous archivist, patiently compiling a layer-by-layer account of Earth's history. This is the world of sedimentary rocks, formed not from fire and pressure, but from the gradual accumulation of sand, silt, clay, and the skeletons of countless organisms in ancient seas, rivers, and lakes. Over millions of years, these loose sediments are buried, compressed, and cemented into stone, creating a striated timeline of past environments. But these layers are far more than just a record of local conditions. They are a finely tuned chronicle of celestial rhythms, capturing the subtle, repetitive beats of planetary motions that have dictated the pulse of our climate for eons. The key to unlocking this cosmic diary lies in a phenomenon known as rhythmic bedding, where the composition or grain size of the rock alternates in a clear, repeating pattern. Imagine slicing into a massive limestone formation and finding an endless stack of delicate pairs, a dark, clay-rich layer followed by a lighter, carbonate-rich layer over and over again like the pages of a book. This isn't random, it's a signal. Each couplet often represents a cyclical shift in climate, frequently tied to what are known as Milankovic Cycles, changes in Earth's orbit and rotation that alter the distribution of sunlight across the globe. These cycles are themselves orchestrated by the gravitational pull of other planets. The slow gravitational tug of war between Jupiter and Saturn, for instance, modulates the eccentricity of Earth's orbit on a 100,000-year cycle, while interactions with Venus gently sway the tilt of Earth's axis every 41,000 years. These astronomical shifts, though slight, have profound consequences. A more circular orbit might lead to a period of stable, mild climate, allowing for the deposition of one type of sediment, while a more elliptical orbit could intensify seasonal contrasts, changing ocean currents and the type of material washing into a basin. The result is a rock formation that behaves like a geological metronome, its rhythmic layers keeping perfect time with the solar system's grand orbital cycles. The famous banded iron formations, with their stunning alternating red and gray bands, are a breathtaking example from Earth's deep past. Each band may represent tens of thousands of years, and their consistent rhythm points directly to a climate system being paced by a celestial clock. Similarly, in more recent geological history, the chalk cliffs of Dover and other Cretaceous deposits show these rhythmic patterns, allowing geologists to literally count the layers and calculate the duration of ancient events with astonishing precision. Beyond the mineral composition, the fossils trapped within these sedimentary pages add another layer of evidence. The types of microscopic plankton found in a layer can tell us about sea surface temperature and nutrient availability at the time it was deposited. A sudden shift in the fossil assemblage, repeating at regular intervals, provides a biological confirmation of the physical rhythmic bedding, painting a vivid picture of how life itself responded to these astronomically driven climate changes. By meticulously measuring the thickness of these rhythmic layers and analyzing their chemical and fossil content, scientists can do more than just read the past. They can identify which specific orbital cycle was dominant at the time the rock formed. This allows them to connect a specific sequence of sedimentary layers to a known period of planetary orbital configuration, effectively using the rock record to calibrate the timeline of celestial mechanics. In this way, a limestone formation in Italy or a shale deposit in the deep ocean becomes a Rosetta Stone, translating the silent, gravitational language of planetary drift into a tangible, earthly history written in stone. While sedimentary rocks chronicle the slow, rhythmic pulse of climate change, igneous rocks capture something far more dramatic and instantaneous: moments of profound planetary stress frozen in time. Born from the fiery depths of the mantle, these rocks whether erupted as lava onto the surface or cooled slowly underground as granite are geological photographs, capturing a precise moment of immense heat and pressure. And increasingly, scientists are discovering that the shutter for these photographs might be tripped not just by forces within the Earth, but by the gravitational hand of the cosmos itself. The very chemistry and timing of these formations appear to be influenced by the subtle, cyclical stresses imposed by the dance of the planets. One of the most powerful celestial influences comes from a source we feel every day: the tides. While we see the ocean rise and fall, the solid ground beneath our feet also experiences these gravitational pulls from the moon and sun, flexing and bending in a rhythm known as earth tides. This constant, gentle squeezing and stretching of the planet's crust, though measured in just centimeters, can act like a periodic trigger on an already pressurized system. It can subtly modulate the flow of heat from the core, influence the convection currents in the malleable mantle, and even affect the pressure within vast underground magma chambers. Research into the timing of volcanic eruptions has begun to show statistically significant correlations with these tidal cycles, suggesting that during periods of high tidal stress, the likelihood of an eruption can be slightly increased. It's as if the moon and sun are gently tapping on the Earth's thermostat, sometimes providing just enough extra nudge to cause a release of pent-up energy that has been building for centuries. But the story goes far beyond daily tides. When we look at the largest volcanic events in Earth's history, cataclysmic episodes that shape the very fate of life on the planet, the timing becomes even more suggestive of a celestial connection. Consider the Siberian Traps, a colossal expanse of igneous rock that covers an area nearly the size of Australia. This formation was created by a series of massive eruptions around 250 million years ago, an event that directly coincided with the Permian-Triassic extinction, the most severe die-off in Earth's history. Similarly, the Deccan Traps in India, another vast volcanic province, erupted with fury around 66 million years ago, right at the time of the Cretaceous-Paleogene extinction that wiped out the dinosaurs. The coincidence in timing is staggering, but the cause of these immense outpourings of lava has long been debated. One compelling theory links these events to the gravitational chaos of planetary drift. Major shifts in the orbits of the giant planets, particularly Jupiter and Saturn, can create resonant gravitational effects that ripple through the entire solar system. These resonances could have perturbed the orbits of asteroids, sending them on collision courses with Earth. The immense energy from such an impact doesn't just create a crater, it sends devastating shock waves around the entire planet. It's believed that the Chicxulub impact, which occurred simultaneously with the Deccan Traps eruptions, may have effectively uncorked the mantle on the exact opposite side of the globe, dramatically amplifying volcanic activity that was already underway. The planetary drift that sent the asteroid our way, therefore, didn't just cause an impact winter. It may have directly triggered a volcanic episode that prolonged the environmental catastrophe for millennia. We can read this story not just in the timing of these events, but in the very chemistry of the rocks themselves. Igneous rocks are like bottled messages from the mantle, and their isotopic composition acts as a unique fingerprint of their source. Elements like strontium and neodymium have different isotopic forms that vary depending on the age and composition of the mantle rock that melted to form the magma. By analyzing these ratios in lava flows from large igneous provinces, geologists can track how the source of the magma changed over the course of the eruptions. Intriguingly, in both the Deccan Traps and the Siberian Traps, the chemistry of the lava shows a clear and rapid shift pathway through the eruptive sequence. This suggests a fundamental change in the mantle source, perhaps as the initial shock of an impact or the sustained stress of a planetary resonance disrupted deeper, more primordial layers of the mantle, bringing a different type of molten rock to the surface. The rocks themselves carry this chemical evidence of a deep Earth suddenly and violently responding to an external trigger. So, the next time you see a photograph of dramatic black basalt columns or hold a piece of rough, crystalline granite, remember that you might be holding a frozen snapshot of a moment when the planets aligned quite literally to reshape our world. These igneous formations are not just monuments to Earth's internal power. They are potential archives of cosmic intervention, recording moments when the gentle, persistent tides of gravitational influence from our celestial neighbors culminated in an outburst of planetary scale change, forever etching their story into the very bedrock of our planet. If igneous rocks are snapshots of fiery moments and sedimentary rocks are patient chronicles of climate, then metamorphic rocks are the ultimate survivors, bearing the scars of unimaginable trials. These are rocks that have been to the brink and back, subjected to the most intense heat and crushing pressure deep within the Earth's crust, yet they did not melt. Instead, they transformed, recrystallizing into something entirely new and magnificently resilient. In their shimmering minerals and banded textures, we find a record of the most profound geological upheavals, events that were not solely driven by Earth's internal engine, but were often orchestrated by the silent, gravitational music of the cosmos. Consider the process of mountain building or orogeny. The Himalayas, the tallest mountains on Earth, are a direct result of the Indian plate colliding with the Eurasian plate. This titanic slow-motion crash, which began around 50 million years ago, pushed ancient seafloor sediments to incredible depths. There, under the immense weight of overlying rock and the geothermal heat of the mantle, these rocks were fundamentally altered. Limestone, once a quiet seabed, became marble. Shale, made of compressed mud, transformed into the glittering, flaky layers of schist or the beautifully banded, high-grade rock known as gneiss. The specific minerals that form under these conditions, like kyanite, staurolite, or garnet, act like a geological thermometer and barometer, telling us the exact temperature and pressure these rocks endured. But what if the timing and intensity of this collision and the metamorphic furnace it created were influenced by forces from beyond our world? This is where the concept of planetary resonances enters the picture. The gravitational pull of other planets, particularly the gas giants, creates subtle rhythmic perturbations in Earth's orbit and rotation. Over millions of years, these resonances can slightly alter the stress fields within the Earth's crust. During a period of enhanced gravitational stress from, say, an alignment of Jupiter and Saturn, the already immense forces driving continental collision might receive a tiny but persistent extra push. This could accelerate the rate of mountain building, forcing rocks deeper and faster, and thus changing the very conditions of their metamorphism. It could also affect the erosion rates on the surface, A shift in climate caused by an orbital change could increase rainfall, washing away rock faster and effectively reducing the pressure on rocks still forming deep below. The metamorphic minerals would record this change in their crystal structure, encoding not just the tectonic event, but a whisper of the celestial rhythm that may have modulated it. The evidence for this lies not just in the minerals themselves, but in their age. When geologists use isotopic dating techniques on metamorphic rocks from major mountain belts around the world, they often find something fascinating. The ages of these intense metamorphic events are not randomly distributed through time. Instead, they appear to cluster at specific periods. One of the most significant clusters aligns with a proposed major episode of planetary migration and gravitational instability in the early solar system known as the Late Heavy Bombardment, around 4 billion years ago. While the most obvious signs of this bombardment are impact craters, the immense energy delivered by these collisions would have also triggered global-scale tectonic shocks and massive metamorphism, effectively cooking the planet's earliest crust. Later clusters, such as those during the assembly of the supercontinent Pangaea, might also be linked to quieter but still influential periods of planetary orbital resonance. By matching the precise ages of metamorphic rocks from different continents with models of solar system dynamics, scientists are beginning to see a potential correlation. It suggests that the great cycles of planetary drift, which rearrange the solar system over hundreds of millions of years, might also be responsible for pacing the great cycles of mountain building and continental transformation here on Earth. The next time you see a piece of gneiss with its elegant, swirling bands, remember that you are looking at more than just a rock. You are looking at a transformed testimony, a piece of Earth's crust that was reshaped by the combined might of our planet's internal forces and the gentle, persistent gravitational nudge from its celestial neighbors. But how do we read the subtle gravitational nudges of distant planets in the very rocks beneath our feet? One of the most astonishing methods involves listening to the Earth's own hidden voice, a magnetic whisper locked inside stone for millions of years. This field of study is called Paleomagnetism, and it transforms ordinary-looking rocks into exquisite cosmic compasses, each one preserving a precise record of where the planet's magnetic poles were located at the moment that rock was born. It's a story written in the language of magnetism, and it begins with tiny, iron-rich minerals like magnetite. When volcanic lava cools or when sediments settle in a quiet sea, these minute mineral grains act like countless tiny needles. As they form, they align themselves with the Earth's magnetic field, and then, as the rock solidifies, they freeze in that orientation forever. It's as if each rock formation has its own internal fossil compass, pointing steadfastly toward a magnetic north that may have vanished eons ago. By collecting samples from rocks of different ages all over the world, scientists can trace the wandering path of the magnetic poles across geological time. This record reveals one of the planet's most dramatic behaviors. The magnetic field doesn't just sit there, it flips. For reasons still not fully understood, the north and south magnetic poles have swapped places hundreds of times throughout Earth's history. These reversals are not random events. When we look at the timeline, we see fascinating patterns. There are long periods called supercrons, where the field remains stable for tens of millions of years without a single flip. And then there are times of incredible turbulence, like during the Jurassic period, when the field seemed to be reversing its polarity in a frantic, chaotic dance. This inconsistency is the first clue that something beyond Earth's core might be at play. If the field's behavior was solely driven by the internal churning of molten iron in the core, we might expect a more regular, predictable pattern. The fact that it isn't suggests an external conductor may be subtly influencing the orchestra. The most compelling hypothesis is that the gravitational influence of other planets can exert a tiny but meaningful pull on the Earth's liquid outer core, the engine that generates our magnetic field. While the core is buried deep beneath thousands of miles of rock, it is still fluid and dynamic. The same tidal forces that flex the solid crust and move the oceans also act upon this vast metallic sea. During periods of particular orbital alignment, or when another planet makes a relatively close pass, something Mars or Venus is capable of over million-year timescales, the additional gravitational stress could potentially disrupt the complex fluid dynamics of the core. This disruption might be just enough to destabilize the magnetic field, triggering a flurry of reversals. Conversely, during times of orbital stability, the core could operate undisturbed, leading to those long periods of magnetic quiet. It's a breathtaking connection. The positions of planets millions of miles away could be imprinted on the magnetic memory of our rocks, influencing one of our planet's most fundamental forces. This magnetic record does more than just hint at celestial influences. It provides a powerful, independent clock for dating global events. The sequence of magnetic reversals is unique, like a barcode etched into time itself. When a new strip of oceanic crust forms at a mid-ocean ridge and records the current magnetic polarity, it creates a symmetrical pattern on either side of the ridge. By matching this barcode from different ocean basins, geologists can piece together the history of seafloor spreading with incredible precision. But the same principle applies to much older rocks on land. If a layer of volcanic ash between sedimentary rocks captures a known magnetic reversal, it can provide an absolute timestamp for the fossils or climate signals found in those layers. This allows scientists to correlate events from different continents and different environments, building a unified, high-resolution timeline of Earth's history. And woven into that timeline are the rhythms of reversal rates, patterns that we can now compare against new models of solar system orbital dynamics. The humble magnetic mineral, once simply a curiosity, has become one of our most reliable guides to understanding not only how the continents have drifted, but how the entire solar system has danced through the ages, its movements quietly recorded in the enduring stone beneath our feet. So if paleomagnetism gives us a global compass and a timeline, then cyclistratigraphy provides the metronome, allowing us to count the beats of that timeline with astonishing precision. This fascinating field turns the layered pages of Earth's sedimentary archives into a finely calibrated cosmic clock. It all begins with a simple but powerful observation. Many rock formations don't just have layers, they have rhythms. They display repeating patterns in their composition, color, or grain size. A dark shale layer, followed by a lighter limestone, then another dark shale, and so on, in a seemingly endless, regular repetition. For a long time, these patterns were seen as a geological curiosity, but we now understand they are anything but random. They are the literal pulse of the planet, a pulse set by the rhythmic gravitational influences of our celestial neighbors. The master clock behind these rhythms is the Milankovic Cycles, named after the Serbian scientist who meticulously calculated how changes in Earth's orbit and rotation affect the amount and distribution of sunlight reaching our planet. There are three primary cycles. First, there's eccentricity, which is the shape of Earth's orbit around the Sun, cycling from more circular to more elliptical over a period of about 100,000 years. Then there's obliquity, the change in the tilt of Earth's axis, which varies between about 22.5 and 24.5 degrees on a 41,000-year cycle. Finally, there's precession, often called the wobble of the axis, like a spinning top slowing down, which affects the timing of the seasons over a 23,000-year cycle. While these are Earth cycles, their pace is not set by Earth alone. The gravitational tug of the other planets, especially the massive Jupiter and Saturn, acts as the timekeeper. Jupiter's immense gravity is the dominant force modulating the 100,000-year eccentricity cycle, while the other planets contribute to the complex interplay that sets the timing for tilt and wobble. Cyclistratigraphers are the detectives who decode these celestial rhythms. They go into the field to immense exposures of sedimentary rock, like the stunning white chalk cliffs of Dover or the layered shale deposits of the American Midwest. They carefully measure the thickness of each couplet, each pair of light and dark layers. By applying advanced statistical analysis to these thickness measurements, they can identify the dominant periodicities. It's not unlike a musician reading sheet music. The thickness variations are the notes, and the statistical analysis reveals the time signature. Finding a strong signal for a 41,000-year cycle in a rock sequence is a powerful indication that the rhythm of Earth's axial tilt was the dominant force controlling climate when those sediments were laid down. This allows them to assign not just relative ages but a duration. If they count 1,000 of these 41,000-year cycles in a rock formation, they can calculate that the entire formation took 41 million years to deposit. This has revolutionized the geologic timescale, transforming it from a relative sequence of events into a high-resolution calendar of deep time. The power of this technique is that it provides a continuous record, filling in the gaps between the discrete points provided by radiometric dating of volcanic ash layers. It allows for incredibly precise correlations between rocks on different continents. A specific pattern of layer thicknesses caused by a particular combination of orbital cycles acts like a unique fingerprint. A geologist in Italy studying limestone deposits in a dried riverbed can match the pattern they see to another geologist working on deep-sea cores drilled from the Pacific Ocean floor. They can say with confidence that this specific dark layer in Italy was formed at the exact same time as that specific dark layer in the Pacific, because both were responding to the same global climate trigger, a slight shift in sunlight caused by the planets aligning in a specific configuration millions of miles away. This turns the entire sedimentary rock record into a synchronized global network of planetary drift monitors. Each rhythmic layer is a data point, a testament to a moment when the gentle, persistent gravity of Jupiter or the precise orbital position of Venus reached across the void and left its subtle mark on the very mud and silt accumulating at the bottom of an ancient sea. While the rhythmic layers of sedimentary rock tell a story of gentle, cyclical change, the geological record also holds evidence of far more violent and instantaneous events that literally came crashing down from the heavens. Impact craters are the solar system's most dramatic punctuation marks, the exclamation points in the story of planetary drift. These colossal scars, formed by the catastrophic collision of asteroids and comets, are not random acts of cosmic violence. Instead, their timing and distribution across Earth, the Moon, and other planetary bodies provide some of the most direct and compelling evidence for how the gravitational dance of the planets has reshaped the inner solar system again and again. To understand this connection, we need to look up from Earth and view our solar system as a single, interconnected gravitational web. The main asteroid belt, that vast field of rocky debris between Mars and Jupiter, and the distant Kuiper belt beyond Neptune, are both filled with countless leftover planetesimals from the solar system's formation. For most of these objects to be dislodged from their stable orbits and sent on a collision course with Earth, something massive has to give them a gravitational shove. That something is almost always the movement of the giant planets. The most famous example of this is the theorized late heavy bombardment, a period around 4 billion years ago when the inner planets were seemingly pummeled by a sudden, intense rain of impactors. The leading explanation for this cataclysm, known as the Nice model, posits that Jupiter and Saturn eventually fell into a specific orbital resonance. This gravitational lockstep between the two giants sent violent ripples through the entire solar system, their immense gravity acting like a paddle in a celestial pond, suddenly flinging swarms of asteroids from the belt inward toward the Sun. The Moon, Mercury, and Mars, with their ancient, airless surfaces, still bear the pockmarked testimony to this event. On Earth, our active geology has erased most of these oldest craters, but the few remaining fragments of crust from that time show signs of being utterly battered. But the story doesn't end 4 billion years in the past. This process of gravitational scattering is ongoing, and we can see its fingerprints on much more recent and biologically significant events. Take the Chicxulub impact crater hidden beneath the Yucatan Peninsula in Mexico. This 150-kilometer-wide scar is the infamous smoking gun for the extinction of the dinosaurs 66 million years ago. The asteroid that created it was a mountain-sized projectile, but where did it come from? Recent dynamical studies suggest it was likely a fragment from a much larger asteroid in the main belt. Computer simulations show that the gravitational influence of Jupiter, and to a lesser extent Mars, can create specific escape hatches in the asteroid belt, orbital pathways where objects are periodically nudged into orbits that cross Earth's path. The timing of the Chicxulub impact may not be a random one-off event, but part of a longer-term cycle of bombardment tied to the rhythmic oscillations of the planet's orbits. In a very real sense, the drift of Jupiter through the solar system may have indirectly signed the death warrant for the dinosaurs. We know these are impact sites and not just ancient volcanoes because of the incredible forensic evidence locked in the rocks. When an asteroid strikes at tens of thousands of miles per hour, it delivers energy equivalent to billions of atomic bombs. This generates pressures and temperatures so extreme that they literally transform matter. Geologists find minerals like stishovite and coesite, which are forms of quartz that only form under the immense pressure of a hypervelocity impact. They find shocked quartz crystals, whose internal lattice structure is crisscrossed with microscopic lamellary parallel lines of deformation that are the mineral's permanent memory of that split-second shockwave. Perhaps the most famous chemical clue is the element iridium. This metal is very rare in Earth's crust but is much more abundant in asteroids and comets. A thin layer of clay rich in iridium has been found in rock sequences all over the world, all dating to exactly 66 million years ago. This global dusting of extraterrestrial material is the ultimate signal that a catastrophic impact event enveloped the entire planet, and it serves as a precise time marker that geologists can use to correlate rock layers from every continent. By identifying these impact layers and precisely dating the craters they are linked to, scientists are building a timeline of terrestrial catastrophe. And when they look at this timeline, an intriguing pattern emerges. It seems that major impact events on Earth might be clustered in time. There appear to be periods of relative quiet and periods where large impacts were more frequent. This clustering is exactly what we would expect if the primary driver of impacts is the gravitational perturbation of the asteroid belt, which itself is governed by the rhythmic, drifting orbits of the giant planets. Each massive crater, from the 2-billion-year-old Vredefort structure in South Africa to the relatively young Barringer crater in Arizona, is more than just a hole in the ground. It is a data point. It is a timestamp of a moment when the unstable dynamics of our solar system reached out and touched Earth with violent force, a permanent scar that links a local catastrophe to a much grander celestial narrative of drifting worlds and gravitational chaos. While the scars of impact craters tell a story of sudden, violent change, the most pervasive and continuous record of planetary influence is written in a far subtler language, the language of atoms themselves. Deep within the chemistry of rocks and ancient ice, stable isotopes act as nature's most precise and unerring environmental sensors, capturing fluctuations in the global climate system that were orchestrated by the slow, gravitational dance of the planets. Unlike radioactive isotopes that decay over time, stable isotopes are permanent. They are different forms of the same element that have varying atomic weights but do not change. This makes them perfect tracers, their ratios shifting in response to environmental conditions and locking that information away in mineral structures for billions of years. Consider the element oxygen, which exists in two common stable forms, oxygen-16, which is lighter, and oxygen-18, which is heavier. When water evaporates from the ocean, the lighter oxygen-16 molecules evaporate more easily than the heavier oxygen-18. Now imagine a shift in Earth's orbit, driven by Jupiter's gravity, that leads to a period of global cooling. More and more of that water vapor, rich in light oxygen-16, gets trapped in growing ice sheets at the poles. This means the ocean water that remains becomes progressively enriched in the heavier oxygen-18. When marine organisms like foraminifera, tiny plankton, build their shells from calcium carbonate, they incorporate the oxygen from this isotopically heavier seawater. When they die, their shells sink and become part of the seafloor sediment, eventually turning into limestone. A scientist drilling a core of that limestone can analyze the ratio of oxygen-18 to oxygen-16 in those fossil shells. A higher ratio doesn't just tell us the water was colder. It provides a precise, quantitative measure of how much water was locked away in ice, directly recording the volume of global ice sheets at the time that shell was formed. Carbon isotopes work in a similar but different way, tracking the planet's biological heartbeat. The vast majority of carbon is carbon-12, with a small fraction being the heavier carbon-13. Photosynthetic organisms like plants and algae have a strong preference for the lighter carbon-12. During periods of high biological productivity, these organisms pull enormous amounts of carbon-12 out of the ocean and atmosphere to build their bodies. When they die and are buried in sediments, they leave the environment around them enriched in the heavier carbon-13. This creates a distinct isotopic signature in marine carbonate rocks. A sudden negative swing in the carbon-13 ratio, however, can signal a catastrophe. If a massive volcanic event or the melting of methane clathrates releases a huge amount of light carbon-12 back into the system, it can overwhelm the natural balance, leaving a sharp negative spike in the rock record that often coincides with mass extinction events. These events themselves can be triggered by the orbital instabilities and impact events that planetary drift causes, linking the geochemical signal directly back to celestial mechanics. The true power of this isotopic detective work emerges when scientists can trace these chemical signals across different types of archives simultaneously. The same orbital cycles that are recorded in the oxygen isotopes of deep-sea limestones are also captured in the air bubbles trapped within ancient ice cores from Antarctica and Greenland. By drilling deep into these ice sheets, researchers can analyze the atmosphere of the past. The bubbles reveal not only the concentration of greenhouse gases like carbon dioxide and methane, but also their isotopic composition, providing a direct readout of past temperature and biological activity. The incredible finding is that the rhythmic patterns seen in the ice cause the cyclical rise and fall of temperatures and gases over the past 800,000 years, match the rhythmic bedding patterns seen in 100-million-year-old limestone formations. They are all responding to the same master clock, the Milankovic Cycles. This creates a seamless chain of evidence, connecting the gravitational nudges of Jupiter and Saturn to changes in Earth's orbit, which then alter climate patterns, which are then faithfully recorded by the isotopic preferences of tiny organisms and trapped in both rock and ice. It proves that the same celestial rhythms that govern the climate cycles of the ice ages also paced the world of the dinosaurs. This geochemical evidence allows us to move beyond simply observing patterns and start understanding the mechanisms. For example, by modeling how a specific planetary configuration would have altered Earth's receipt of solar energy, and then matching that model's predicted climate outcome to the isotopic data stored in rocks of that age, scientists can test and refine their theories of solar system evolution. A layer of rock with a specific isotopic signature becomes a calibration point for a celestial event. It transforms abstract gravitational models into tangible, earthly history, written not in words, but in the precise and unchangeable ratios of atoms that were present when the rock was formed. This is how the silent, invisible force of planetary drift finds its voice, speaking through the chemical clues left in the most unassuming stones. Yet the story of life written in stone goes far beyond the simple rise and fall of species. It captures the very rhythm of existence, a rhythm often conducted by the distant, gravitational hands of the planets. Fossils are not merely the remains of ancient life. They are biological echoes of celestial cycles, preserving within their forms and distributions a direct record of how life on Earth has pulsed in time with the solar system's grand orbital metronome. When we look at a succession of fossils in a layered rock formation, we are not just seeing a parade of evolutionary change. We are reading a chronicle of how cosmic forces have shaped the destiny of every living thing. Consider the humble foraminifera, tiny single-celled plankton with intricate shells that have been abundant in the oceans for hundreds of millions of years. When these creatures die, their shells rain down onto the seafloor, accumulating in countless numbers to form thick layers of limestone. Paleontologists can take a core sample of this limestone and, layer by layer, analyze the different species of forams present. What they find is a stunningly precise record of changing ocean temperatures. During a period of an orbital cycle that brings cooler temperatures, species adapted to cold water will dominate the assemblage. As the cycle shifts towards a warmer phase, warm water species will take over. The fossil record of these microscopic organisms is so detailed and continuous that it allows scientists to track the 41,000-year cycle of Earth's axial tilt and the 100,000-year cycle of orbital eccentricity with incredible precision. The life and death of these tiny creatures preserved in stone became an exquisitely sensitive thermometer, recording the climatic consequences of planetary drift. This celestial influence extends to the most dramatic chapters in life's history, mass extinctions and rapid explosions of new life. While a single asteroid impact might deliver the final blow, the stage is often set by longer-term climate changes driven by orbital shifts. The end of the Triassic period, for instance, saw a massive die-off that cleared the way for the rise of the dinosaurs. This extinction event coincides with a period of immense volcanic activity, but the environmental chaos that made life so difficult was likely amplified by a planetary configuration that pushed Earth's climate into extreme volatility. The fossil record shows not a single instant of death, but a prolonged period of stress where certain species gradually disappear, a pattern that suggests a deteriorating environment over many thousands of years, perfectly in line with the slow, grinding pace of orbital change. On the other side of catastrophe, we see the opposite effect. The recovery and rapid diversification of life after an extinction event, known as adaptive radiation, also appears to be paced by these astronomical rhythms. As the climate stabilizes into a new, predictable pattern dictated by orbital cycles, life finds new opportunities, new ecological niches open up, and the fossil record reveals a sudden blossoming of new forms and species, all evolving to fill the vacant spaces in a world recovering its balance. The cycles of destruction and creation, of extinction and speciation, are therefore not random. They are, in part, a biological response to a climate system being tuned by the gravitational music of the planets. The bones of a dinosaur, the shell of an ammonite, the leaf imprint of an ancient plant, each one is more than a relic. It is a data point in a vast biological dataset that records the cosmic influences on our planet's habitability. By reading this biological archive alongside the chemical and physical ones, we gain a profoundly unified view of Earth's history, where the story of life and the story of the heavens are inextricably and beautifully intertwined. But to truly grasp the universal nature of these processes, we cannot look at Earth alone. Our planet is just one chapter in a much larger story, and to read that story in its entirety, we must become comparative planetary geologists, turning our gaze to our nearest celestial neighbors, the Moon and Mars. These worlds, though seemingly alien, hold their own rock records that act as independent witnesses to the same grand narrative of solar system evolution, free from the constant recycling and erosion that have reshaped so much of our own planet's surface. By studying the stones of other worlds, we gain a powerful cross-check dataset, allowing us to separate what is uniquely Earth story from what is a universal signature of planetary drift. The Moon, our silent companion, is a museum of the solar system's violent youth. The lunar samples brought back by the Apollo astronauts are nothing short of geological treasure, providing a pristine, airless record of events that have long been erased on Earth. When we analyze these rocks, we find that the Moon's surface is incredibly ancient, with vast plains of volcanic basalt, known as Maria, that solidified between 3 and 4 billion years ago. But more importantly, the Moon is covered in a layer of pulverized rock called regolith, and within it, the timing of the most intense cratering is meticulously preserved. The density and distribution of these craters tell a clear story. A cataclysmic spike in impacts around 3.9 billion years ago, a period we call the Late Heavy Bombardment. This lines up perfectly with dynamical models like the NICE model, which suggest that the gravitational migration of Jupiter and Saturn sent a shockwave of debris through the inner solar system at that exact time. The Moon's scarred face is the ultimate proof that this event was real, and not just a theoretical idea. It provides a precise calendar for a major episode of planetary drift, an event that also battered the young Earth and likely delivered the very water that fills our oceans today. Mars, the red planet, tells a different but equally compelling chapter of the story. While we don't yet have curated samples from Mars, we have the next best thing: meteorites that were blasted off its surface by impacts and eventually found their way to Earth. We also have an incredible wealth of data from rovers like Curiosity and Perseverance, which have been acting as robotic field geologists, scrutinizing sedimentary layers and ancient river deltas up close. This data paints a picture of a world that was once dramatically different, a planet with flowing water, lakes, and a thicker atmosphere. What caused Mars to transform into the cold, dry desert we see today? The answer appears to be a combination of losing its protective magnetic field and profound climate shifts, and those climate shifts may have been driven by changes in its orbit. Martian rocks show evidence of rhythmic layering similar to Earth's Milankovic cycles, but with different periodicities due to Mars's unique orbital characteristics and its two small, oddly shaped moons, Phobos and Deimos. Furthermore, satellite observations have detected strange, stripe-like magnetic anomalies in the ancient southern highlands of Mars, suggesting it once had a magnetic field that generated in a plate tectonic-like manner before shutting down. This provides a crucial point of comparison. By seeing how another rocky planet's internal engine and climate responded to celestial forces, we can better understand the range of possible outcomes and what makes Earth's ongoing geological activity so special. This comparative approach is what truly unlocks the mystery. When we place the lunar record of bombardment, the Martian record of climate change, and Earth's own complex geological archive side by side, common patterns begin to emerge. We see that the gravitational influence of the gas giants, particularly Jupiter, didn't just affect Earth, it orchestrated a symphony of change across the entire inner solar system. A resonance between Jupiter and Saturn might have triggered the late heavy bombardment that pockmarked the Moon and Mars at the same time. A shift in Jupiter's orbit could have altered the flux of comets from the outer solar system, affecting the delivery of water and organic materials to both Earth and Mars. By having these multiple planetary diaries to read, we can triangulate the truth, moving from suggestive correlations on a single world to confident, solar system-wide conclusions. The rocks of the Moon and Mars act as independent verification, confirming that the story of planetary drift written on Earth is not a local legend, but a fundamental epic of our celestial neighborhood, with each world adding its own unique verse to the same cosmic song. Now, let's tune our ears to the subtle harmonies of the solar system, to the gravitational rhythms known as orbital resonances. Imagine two planets locked in a celestial dance, their orbits syncing up in a precise mathematical ratio, like two pendulums swinging in perfect time. Every few orbits, one planet gives the other a consistent gravitational tug, and over millions of years, these tiny, rhythmic nudges can accumulate into a powerful force that leaves a lasting signature deep within the rock record. It's not a chaotic pull, but a repeated, predictable influence, and Earth's geology has been listening to this cosmic music for eons. One of the most fascinating potential resonances involves our planetary neighbor, Mars. While they may seem distant from each other now, their orbits have not always been fixed. As the giant planets drifted in the early solar system, they could have pushed and pulled the inner worlds into temporary rhythmic locksteps. Models suggest that Earth and Mars may have periodically fallen into a resonance where their orbital eccentricities were amplified in a coordinated cycle. For Earth, this would have meant a rhythmic pulsing of its orbit, making it slightly more elliptical on a regular schedule of about 2.4 million years. A more elliptical orbit means more variation in the distance from the Sun throughout the year, which translates to stronger seasonal contrasts. During the phase of maximum eccentricity, summers would be hotter and winters colder in each hemisphere. This astronomical shift from a near-perfect circle to a slightly more oval-shaped path, repeated every 2.4 million years, acts as a metronome for Earth's climate system. The increased solar radiation during the intense summer periods can dramatically accelerate the melting of ice sheets, while the more extreme seasonal shifts alter global precipitation patterns and ocean currents. These changes are not lost on the silent, patient processes of sedimentation. In regions like the deep ocean basins or the ancient Mediterranean Sea, the rate at which clay, silt, and microscopic plankton skeletons settle to the seafloor is directly controlled by climate. During a high eccentricity phase, enhanced weathering on continents might wash more sediment into the oceans, creating a thicker, perhaps chemically distinct, layer of rock. During a quieter, more circular orbital phase, sedimentation might slow, depositing a thinner, different layer. Over millions of years, this creates a rhythmic pattern in the rock itself, a series of thick, thin, or dark light couplets that a geologist can measure, and within that pattern, they can find the precise 2.4 million year beat. Finding this beat requires incredible detective work. Scientists drill deep into the ocean floor to extract long cores of layered sediment, or they trek to exposed cliff faces that were once ancient seabeds. They then use sophisticated techniques to analyze the chemical and physical properties of each microscopic layer, building a dataset that spans millions of years. By applying mathematical tools like spectral analysis to this data, they can search for hidden periodicities repeating signals buried within the noise of random geological events. And they have found it in sediments from the Mediterranean dating back millions of years and in deep sea cores from various oceans. That 2.4 million year cycle emerges from the data with striking clarity. It is the fingerprint of a gravitational conversation between Earth, Mars, and the distant giants like Jupiter that orchestrate the rhythm from afar. The evidence is not just in the physical layers of rock, but also in their chemical makeup. The same orbital resonance that affects climate also influences geochemical cycles. For instance, periods of increased eccentricity and intensified weathering can flush more nutrients into the oceans, affecting biological productivity. This, in turn, is recorded in the isotopic ratios of carbon and oxygen within the fossils found in those sedimentary layers. A shift in the ratio of carbon-13 to carbon-12 might indicate a burst of biological activity triggered by the orbital pulse. Therefore, the resonance leaves a multifaceted imprint, a physical rhythm in the layer thickness, a chemical rhythm in the isotopes, and a biological rhythm in the fossil assemblages. By combining all these lines of evidence, geologists can trace the faint but undeniable fingerprints of planetary drift, revealing how the gentle, repetitive harmonies of celestial mechanics are composed into the very stone beneath our feet, a slow and majestic symphony written over millions of years. But to truly appreciate the scale of this celestial influence, we must turn our attention to the solar system's undisputed gravitational titan, Jupiter. This colossal gas giant, with a mass more than twice that of all other planets combined, acts as a gravitational anchor and a chaotic disruptor, its immense pull weaving a complex signature into the very fabric of our planet's geological history. Its role is not that of a distant, passive observer, but an active and forceful participant in the solar system's evolution, a force whose movements have dictated the fate of countless asteroids, sculpted the orbits of its planetary neighbors, and left a permanent record in the stones beneath our feet. The story begins in the solar system's violent infancy with a dramatic journey known as the Grand Tack Model. This theory suggests that in the first few million years after its formation, Jupiter did not remain in a stable orbit. Instead, it embarked on a monumental migration, plunging inward toward the Sun, pulled by gravitational interactions with the gaseous protoplanetary disk. It traveled as far inward as the orbit of present-day Mars before a gravitational tug of war with Saturn pulled it back outward to its current position. This cosmic yo-yo act had catastrophic consequences for the inner solar system. Jupiter's immense gravity acted like a gravitational wrecking ball, violently scattering the primordial asteroid belt and hurling a vast swarm of planetesimals and comets inward. This event is a leading candidate for triggering the late heavy bombardment, that period of intense asteroid impacts that pockmarked the Moon and the young Earth around 4 billion years ago. The evidence for this isn't just theoretical, it's locked in the oldest rocks we can find. Zircon crystals from that era show shock features and isotopic anomalies consistent with a massive influx of extraterrestrial material, while the sheer age distribution of impact craters across the solar system aligns with the timing of this proposed planetary migration. Jupiter's early wanderlust essentially set the stage for Earth's subsequent geological and even biological evolution by delivering both water and volatile elements through this celestial bombardment. Even after settling into its current orbit, Jupiter's influence did not diminish. It simply became more rhythmic and periodic. Its immense gravity continues to exert a steadying yet modulating hand on Earth's long-term climate cycles. The planet is the primary pacemaker for the longest of the Milankovic cycles, the 400,000-year and 100,000-year eccentricity cycles, which describe the shape of Earth's orbit around the Sun. Jupiter's gravitational tug slowly stretches and contracts Earth's orbital path from a near-perfect circle to a slight ellipse and back again. This rhythmic alteration directly controls the amount of solar energy our planet receives over these vast timescales, driving the pulse of the ice ages. The record of these cycles is exquisitely preserved in the rhythmic layering of sedimentary rocks across the globe. The alternating dark and light bands in formations like the chalk cliffs of Dover or the layered shales of the Mediterranean are a direct transcription of Jupiter's gravitational influence, a slow, celestial heartbeat captured in stone. By measuring the thickness of these layers, geologists can effectively chart the historical changes in Earth's orbit, a change dictated primarily by the persistent pull of the solar system's largest planet. Beyond shaping our orbit and climate, Jupiter also acts as the solar system's primary gatekeeper, controlling the flow of extraterrestrial debris that reaches Earth. Its gravity creates stable and unstable regions within the asteroid belt, effectively opening and closing gravitational channels that allow asteroids to be nudged into Earth-crossing orbits. Scientists can track this changing flux not from craters alone, but from the chemistry of the rocks themselves. Ancient deep-sea sediments, which accumulate very slowly and evenly, act like a continuous tape recorder of dust falling from space. Within these sediments, geologists find traces of rare elements like iridium and osmium, which are far more abundant in asteroids than in Earth's crust. By analyzing the concentration of these extraterrestrial fingerprints over time, researchers have detected periods of significantly higher asteroid dust influx, suggesting times when Jupiter's gravitational influence was particularly effective at stirring up the asteroid belt and sending material our way. The very air we breathe, or rather the noble gases trapped within ancient rocks, also tells a story. Isotopes of helium and neon found in ancient sedimentary layers can have ratios that point to a cosmic, rather than terrestrial, origin. Fluctuations in the concentration of these gases over millions of years provide another indirect record of how much cosmic dust was raining down on Earth, a process heavily influenced by the giant planet's gravitational sway. When we piece together all this evidence, the ancient impact scars, the rhythmic sedimentary layers, and the subtle chemical fingerprints of cosmic dust, a profound picture emerges. Jupiter is not a silent, distant king, but an active sculptor of Earth's deep history. Its dynamic past initiated a bombardment that may have delivered the building blocks of life and shaped our early crust. Its present gravitational dominance sets the metronome for our climate's most profound rhythms, rhythms faithfully recorded in the layered archives of sedimentary rock. And its ongoing role as celestial traffic cop regulates the stream of extraterrestrial material that continually falls upon our world, leaving a faint but detectable chemical signature. To study Earth's rocks is, in a very real sense, to listen to the echo of Jupiter's immense gravity, a force that has been weaving its story into our own for over 4.5 billion years. While Jupiter's immense gravity orchestrates the solar system from a distance, the relationship between Earth and its closest planetary neighbor, Venus, is far more intimate. A gravitational tango between two worlds so similar in size and composition that they are often called twins. Yet for twins, their fates diverged wildly, One became a lush, living world, the other a scorching, acidic inferno. Despite their different destinies, their histories are deeply intertwined, not just by proximity, but by a constant, silent gravitational conversation that has subtly shaped the geological and climatic story of both planets for billions of years. This celestial partnership means that the rocks beneath our feet may hold clues not only to Earth's past, but to the evolution of our mysterious sister world. This ongoing dialogue operates through the mechanism of orbital resonance. Just as repeatedly pushing a child on a swing at just the right moment amplifies their arc, the gravitational pull between Earth and Venus can give each other's orbits a periodic nudge. The two planets fall into a rhythmic alignment approximately every 0.8 years, a cycle where their gravitational influences reinforce each other. Over immense timescales, these repeated, tiny tugs can accumulate, potentially altering the eccentricity, the ovalness of each other's orbits. Even a slight change in Earth's orbital shape can have profound consequences, affecting the intensity of seasons and the long-term stability of ice ages, rhythms we can read in the layered sedimentary records of our own planet. But the influence may reach even deeper, past the climate and into the very fires of the Earth itself. Some planetary scientists propose that these resonant gravitational stresses could act on Earth's interior, providing a small but persistent trigger for volcanic activity. The immense tidal forces flexing the solid crust might also create minute fluctuations in pressure within the malleable mantle, potentially influencing the rise of massive mantle plumes. These superheated columns of rock are the source of Earth's largest volcanic events, the large igneous provinces that have, throughout history, dramatically altered the climate and caused mass extinctions. Intriguingly, when researchers model the orbital paths of Earth and Venus back in time, they find that periods of known massive volcanism on Earth, such as the eruptions that created the Deccan traps 66 million years ago, sometimes coincide with eras of particularly close approaches or strong resonant interactions with Venus. It's a compelling, though still debated, idea that the gravitational nudge from our sister planet might have helped uncork the mantle, releasing planet-altering volumes of lava whose evidence is now frozen into vast basalt formations. Understanding this potential link makes the exploration of Venus itself not just a mission to another world, but a crucial journey to read the missing pages of Earth's own history. While Venus's surface is shrouded in a thick, crushing atmosphere of carbon dioxide, radar maps from missions like Magellan have pierced the clouds to reveal a geological wonderland, a surface dominated by volcanic features, vast plains of basalt, and strange, deformed mountain belts called tessera that may be the closest analog to Earth's own continents. There is compelling evidence that Venus once had vast oceans of water, much like early Earth, before a runaway greenhouse effect boiled them away. The planet may have even experienced a form of plate tectonics in its distant past before its surface locked up into a single, stagnant lid. The chemical composition of Venusian rocks, though inferred remotely, suggests a volcanic history that could have parallels to our own. By comparing the timing of major resurfacing events on Venus, where huge lava flows erased older features, with periods of intense geological activity on Earth, scientists hope to find a common rhythm, a pulse of inner solar system activity that affected both worlds simultaneously, driven by their shared gravitational dance. This comparative planetology transforms every new discovery about Venus into a key for decoding our own planet. The Venus Express and upcoming missions like Veritas and Da Vinci Plus aim to map the Venusian surface in greater detail and even analyze its atmosphere for clues of past water and ongoing volcanic activity. Finding evidence of recent volcanism on Venus would be a revelation, suggesting it is still a geologically active world. If that activity can be linked to specific orbital configurations with Earth, it would provide powerful support for the idea that the gravitational interplay between planets is a fundamental driver of geological change. The rocks of Earth, therefore, are not an isolated record. They are one half of a conversation, a diary whose entries about climate shifts, volcanic fury, and tectonic upheaval may find their echo in the scorching, volcanic plains of our celestial twin. By learning to read both books side by side, we begin to see the true narrative of the inner solar system, a story of two worlds, forever linked by gravity, dancing through time and shaping each other's destinies in ways we are only just beginning to understand. While the gravitational dance of the inner planets writes its story in climate cycles and volcanic events, the true scope of planetary drift extends far beyond the realm of rock and gas giants into the dark, frozen frontier of our solar system. Out past the orbit of Neptune lies a vast, diffuse reservoir of primordial ice and rock known as the Kuiper Belt. This distant domain is not a static wasteland. It is a gravitational echo chamber where the movements of the outer planets create ripples that eventually, over millions of years, travel inward to leave their mark on our own world. The story of how these icy bodies at the solar system's edge connect to the geology of Earth is one of the most fascinating and long-distance relationships in all of science. This connection operates like a game of cosmic pinball, with Neptune acting as the primary flipper. As the solar system evolved, the giant planets migrated outward to their current positions. Neptune's journey through the primordial Kuiper belt was anything gentle. Its immense gravity scattered countless icy bodies in all directions. Many were flung outward into the even more distant Oort cloud, but a significant number were sent careening inward into the realm of the giant planets. Through a complex series of gravitational hand-offs between Jupiter, Saturn, and Uranus, some of these objects were eventually set on a path straight into the inner solar system, transforming from quiet Kuiper belt objects into spectacular, vaporizing comets. Each time one of these comets plunges toward the Sun, it leaves behind a trail of dust and debris, and if its path crosses Earth's orbit, that material rains down upon our planet as a constant, faint drizzle of extraterrestrial dust. But sometimes the delivery is far more dramatic than a gentle drizzle. Gravitational models suggest that Neptune's orbit itself undergoes slow, cyclical changes due to its interactions with the other giant planets. During periods when its orbit becomes more elliptical or slightly inclined, its gravitational influence can shake the Kuiper belt more vigorously, potentially dislodging a whole swarm of objects at once. This can trigger a comet shower, a significant increase in the number of comets entering the inner solar system over a period of a few 100,000 years. The evidence for such an event isn't just theoretical, it's written in the chemistry of our rocks. Geologists studying sedimentary layers from the Ordovician period, around 460 million years ago, have found a layer with a pronounced anomaly in the isotopes of helium. The specific ratio of helium-3 to helium-4 they discovered is incredibly rare on Earth, but is a known signature of extraterrestrial material, particularly the type of pristine, ancient dust found on comets. This helium spike is interpreted as the chemical fingerprint of a major comet shower, a period when Earth was bombarded with an unusually high amount of cosmic dust from a disturbance that began in the Kuiper belt, billions of miles away. The influence of these distant realms isn't limited to catastrophic impacts or dustings of exotic elements. The same gravitational interactions that govern the orbits of the outer planets operate on mind-bogglingly long timescales, creating cycles that last for millions of years. These grand cycles can subtly influence the stability of Earth's own orbit over epochs. While the inner planets set the rhythm for our 100,000-year ice age cycles, the slow, gravitational tug of war between Jupiter, Saturn, Uranus, and Neptune can impose a much slower, deeper beat on the solar system. This supercycle might gently modulate the eccentricity of Earth's orbit over millions of years, leading to exceptionally long periods of climatic stability or, conversely, prolonged instability. These multimillion-year trends would be recorded not in the fine, rhythmic layers of a limestone bed, but in much broader patterns in the geological record, extended eras of widespread aridity or humidity that affected global sedimentation patterns, the formation of vast deserts or coal swamps, and the long-term rise and fall of sea levels. The very fact that we can identify these supercycles in the rock record suggests that the architecture of the entire solar system, from its heart to its frozen outer fringe, is involved in writing Earth's deep history. The Kuiper belt, therefore, is more than just a collection of icy leftovers. It is a gravitational reservoir, a storage of momentum, and a source of perturbation whose dynamics, initiated by the drift of the outer planets, ultimately echo through the void to inscribe their subtle signature on the stone tablets of our world. Now let's zoom in on the master clock itself, the celestial metronome that has been ticking with unwavering precision for hundreds of millions of years, setting the rhythm for ice ages, evolutionary leaps, and the very deposition of the rocks we walk upon. These are the Milankovic cycles, the grand astronomical cycles that act as the primary pacemakers of our planet's climate and geological processes. They are the direct physical mechanism through which the subtle gravitational pull of other planets is translated into a language that Earth's rocks can understand and record. Named after the Serbian scientist Milutin Milankovic, who painstakingly calculated their complex mathematics in the early 20th century, these cycles describe the predictable, rhythmic changes in three key aspects of Earth's journey around the Sun: its orbit, its tilt, and its wobble. The first of these is eccentricity, which describes the shape of Earth's orbit. Think of it not as a perfect circle, but as an oval that slowly becomes more or less stretched over time. This cycle, shifting between a more circular and a more elliptical path, operates on two main time scales, 100,000 years and 400,000 years. When the orbit is more elliptical, Earth receives significantly more solar energy when it is closest to the Sun, intensifying seasonal contrasts. The primary gravitational force behind this slow stretching and contracting of our planetary path is none other than the immense bulk of Jupiter and Saturn. Their relentless tug of war with our planet is what dictates this longest and most powerful of the astronomical rhythms. Next is axial tilt, or obliquity. This is the angle at which Earth's axis is inclined relative to its orbital plane around the Sun. It's this tilt that gives us our seasons, but this angle is not fixed. It gently rocks back and forth between about 22.1 and 24.5 degrees over a consistent cycle of 41,000 years. A greater tilt means more extreme seasons, hotter summers, and colder winters in both hemispheres. A lesser tilt leads to milder seasons and, crucially, cooler summers at high latitudes that are less effective at melting winter snow, allowing ice sheets to gradually accumulate over millennia. This wobble of the axis is influenced by the gravitational influences of other planets, much like the gravity of the Moon and Sun cause the precession of the axis. That precession, often called the precession of the equinoxes, is the third cycle. Imagine Earth's axis is like a spinning top that is slowly wobbling in a circle. This wobble, which completes a full cycle about every 23,000 years, changes the timing of the seasons relative to Earth's position in its orbit. It determines whether a given hemisphere is pointed toward the Sun at its closest approach, leading to a very hot summer, or at its farthest point, resulting in a milder summer. This cycle is primarily driven by the gravitational pull of the Sun and the Moon on Earth's equatorial bulge. The true magic happens when we see how these three cycles combine. They overlap and interfere with each other, sometimes amplifying their effects to plunge the planet into an ice age, and at other times cancelling each other out to create a long period of interglacial warmth. This complex interplay is the fundamental driver of the Quaternary ice ages that have characterized the last 2.6 million years of Earth's history. But their influence extends far deeper into the past, and it is within the layered archives of sedimentary rock that we find their most compelling and beautiful testimony. Geologists searching for this evidence look for a phenomenon known as rhythmic bedding. In many sedimentary formations, they find a stunningly regular repetition of rock type, color, or grain size. A classic example can be found in the Cretaceous rocks of Italy, in a formation known as the Cisti of Fucoides. Here you can see pairs of layers, a darker, organic-rich shale followed by a lighter, carbonate-rich limestone, repeated over and over again like the pages of a book. Each couplet is believed to represent a 20,000-year precessional cycle. The darker shale layer was likely deposited during a wetter, cooler period with higher organic productivity, while the lighter limestone formed during a drier, warmer phase. By simply counting these layers, scientists can measure the passage of deep time with astonishing accuracy, turning a cliff face into a calendar counting off the millennia. This isn't limited to ancient seafloors. Immense deposits of wind-blown silt called loess, found in China and the American Midwest, also show this rhythmic patterning. The alternating light and dark bands within these deposits correspond to dry, dusty glacial periods and wetter, more stable interglacial periods, perfectly paced by the Milankovic cycles. Even fossilized coral reefs act as paleontological dipsticks. Corals grow daily bands, and their annual growth patterns change in response to water temperature and sunlight. By analyzing the thickness and chemistry of these bands in ancient corals, scientists can detect the fingerprints of precessional and tilt cycles that affected the climate tens of millions of years ago. By decoding these patterns, geologists do more than just confirm a theory. They unlock a powerful tool for calibrating the geological timescale. The rhythmic layers provide a continuous, high-resolution timeline that fills the gaps between the discrete points in time provided by radiometric dating of volcanic ash layers. If you know a set of 10 layers was deposited over 100,000 years, you can calculate the rate of sedimentation and assign a precise duration to geological events captured within that rock sequence. This allows for incredibly precise correlations between rocks on different continents, creating a globally synchronized record of Earth's history. These cycles are the reason we can say with confidence that a volcanic eruption in India happened at the exact same time as a mass extinction in the Atlantic Ocean. The rocks, through their rhythmic language, have become the most reliable cosmic clocks we have. Their steady tick a direct echo of the gravitational music of the spheres. But perhaps the most profound planetary geological connection of all involves the very air we breathe, a revolution in Earth's atmosphere triggered by life itself, yet potentially set in motion by the silent mechanics of the solar system. Around 2.4 billion years ago, our planet underwent a transformation so radical, it is known as the Great Oxidation Event, a period when oxygen, a toxic waste product to most life at the time, began to accumulate in the atmosphere for the very first time, forever changing the chemical destiny of our world. For decades, the cause of this event was seen as a purely biological story, the triumph of cyanobacteria, the first organisms to master the art of photosynthesis. But newer evidence suggests this biological revolution may have received a crucial and cosmic push from the drifting of the planets. The key to this celestial connection lies in the intricate dance between climate, rocks, and life. The cyanobacteria producing the oxygen had been around for hundreds of millions of years before the event, but their oxygen was quickly mopped up by vast amounts of dissolved iron in the oceans and gases like methane in the atmosphere. For oxygen to permanently build up, this chemical sink had to be filled, and that required a massive and sustained increase in photosynthetic activity. This is where planetary drift may have played a decisive role. Gravitational interactions, particularly between Jupiter and Mars, could have nudged Earth's orbit into a period of heightened eccentricity or shifted its axial tilt. Even a small change in these orbital parameters would have significantly altered the distribution of sunlight across the globe, potentially intensifying seasonal monsoon rains and increasing continental weathering. Imagine a world where orbital shifts lead to heavier, more consistent rainfall. This rainwater, slightly acidic from carbon dioxide in the atmosphere, would have relentlessly washed over the barren volcanic landscapes of the early Earth, breaking down rocks and flushing unprecedented amounts of vital nutrients, especially phosphorus, into the ancient oceans. Phosphorus is a key ingredient for life, a fundamental component of DNA and the energy currency of cells. This sudden, nutrient-rich deluge would have been like a global fertilizer event, triggering an explosive bloom of cyanobacteria in the shallow seas. Their populations would have skyrocketed, pumping out oxygen at a rate that finally overwhelmed the planet's natural chemical sponges. The evidence for this lies in the very rocks that define the era, banded iron formations. These stunningly beautiful rocks, with their alternating layers of red jasper and shiny gray iron minerals, are the direct result of this process. They formed as the newly abundant oxygen produced by the blooming bacteria reacted with the dissolved iron in the oceans, causing it to rust and settle to the seafloor in immense, rhythmic layers. The most compelling clue for a celestial trigger comes from the subtle chemistry locked within these ancient rocks. Geologists analyzing isotopic ratios of elements like sulfur and carbon from this time period have found strange and abrupt fluctuations. These anomalies are signatures of a biosphere in sudden, dramatic upheaval, and intriguingly, their timing appears to be periodic. They don't suggest a single, sudden biological invention, but rather a series of pulses, of stops and starts in the oxygenation process. This pattern of fits and starts aligns beautifully with the idea of orbital forcing. It suggests that the gravitational influences of other planets were modulating Earth's climate in cycles, alternately creating conditions perfect for bacterial blooms and then shutting them down, repeatedly pushing the atmosphere toward a permanent tipping point. The Great Oxidation event, therefore, may not have been a single switch being flipped, but a dimmer switch being slowly turned up, with the hand on that switch belonging to the rhythmic gravitational dance of our celestial neighbors. This convergence of evidence, the isotopic signals, the timing of the nutrient pulses, and the climatic models of orbital change, paints a breathtaking new picture of one of Earth's most pivotal moments, revealing a world where the drift of planets millions of miles away helped clear the air for the future of life itself. Now, let's journey to one of the most extreme and captivating chapters in Earth's deep history, a time when the entire planet may have become a glistening, frozen snowball, its oceans sealed under a mile-thick layer of ice from the poles all the way to the equator. These are the Snowball Earth events, and while they sound like the plot of a science fiction film, the geological evidence for them is written plainly in the rocks. The concept is staggering, a runaway feedback loop where expanding ice sheets reflect more and more sunlight back into space, plunging the planet into a deep freeze so profound that it nearly ended life itself. But what could possibly trigger such a global catastrophe? And even more puzzling, how did the planet ever recover? The answers, it seems, are written not just in the ice, but in the stars, with the subtle gravitational nudges of planetary drift potentially providing the push that started and ended this incredible deep freeze. The initiation of a snowball Earth likely required a perfect and terrible storm of conditions. Our planet has a natural thermostat, but it can be overridden. If continental landmasses happen to cluster around the equator, their bright, rocky surfaces can reflect more sunlight than dark, heat-absorbing oceans would, creating a slight cooling effect. Into this already cool world, a powerful volcanic eruption could spew immense amounts of sunlight, blocking sulfate aerosols into the stratosphere. But the final, critical push may have come from above. This is where the Milankovic cycles, those rhythms paced by planetary gravity, come into play. If Earth's orbit was in a phase of low eccentricity, meaning it was nearly circular, it would receive a very stable but overall weaker amount of solar energy throughout the year. Combine this with a period of low axial tilt, which would mean less extreme seasons and particularly mild summers at high latitudes, and you have a recipe for disaster. Snow that falls in the winter doesn't melt in the summer. It accumulates season after season, millennium after millennium. The ice sheets begin to creep down from the poles. As they expand, they reflect more sunlight, which cools the planet further, which expands the ice even more. This is the albedo feedback loop, and once it passes a critical threshold, it can race out of control, plunging the entire planet into the icehouse in a geological blink of an eye. The evidence for this frozen world is etched into the geology of every continent. Geologists find ancient glacial deposits, called tillites, made of jumbled rock and debris that was once carried by glaciers, in places that are now tropical, like the deserts of Namibia and the outback of Australia. These aren't just any glacial deposits, they are found at sea level, proving the ice sheets that dropped them were not alpine glaciers but massive continental ice sheets that reached the ocean. But the most telling evidence lies just above these glacial layers. In a seemingly impossible sequence, the stark evidence of ice is directly overlain by thick layers of limestone, known as cap carbonates. These rocks form in warm, shallow seas, not on a frozen globe. This bizarre juxtaposition is the key to the entire Snowball Earth story. It tells us that the freeze was followed by an incredibly rapid and intense greenhouse period. The most well-dated of these events, the Sturtian glaciation, began with shocking speed around 717 million years ago, and its timing is incredibly suggestive. This period aligns with models of what Earth's orbital parameters might have been like, influenced by the gravitational pull of other planets. It also coincides with the breakup of the supercontinent Rhythmic, which would have placed continents in the tropics, and volcanic activity would have been high, setting the stage for that perfect storm. So how do you break a snowball if the entire planet is covered in ice, reflecting almost all sunlight? How does it ever heat up again? The escape hatch is the planet's own internal heat. Volcanoes don't care about the weather on the surface. They continue to erupt, relentlessly pumping vast quantities of carbon dioxide into the atmosphere. On a normal planet, this CO2 is absorbed by rocks and oceans through weathering. But on a snowball Earth, the chemical weathering process grinds to a halt because the water is locked up in ice. With no way to remove it, the CO2 from volcanoes simply builds up in the atmosphere over millions of years, creating an incredibly powerful greenhouse effect. Eventually, after perhaps 10 or 15 million years of buildup, the concentration of CO2 becomes so high that it overwhelms the ice's reflectivity. The thaw, when it comes, is not gradual. It is catastrophically fast, geologically speaking. The ice melts rapidly, and the planet rockets from a deep freeze into a scorching greenhouse. The proof of this sudden inferno is the cap carbonate. As the ice melts, the oceans are suddenly exposed to an atmosphere with extremely high CO2. They become highly acidic and suck up enormous amounts of carbon, precipitating it out as those massive layers of limestone that directly cap the glacial deposits. The entire incredible cycle from freeze to fire is recorded in the geochemistry of the rocks. During the frozen period, the biological pump that normally cycles carbon is shut down. This leaves a unique signature in the carbon isotopes of any sediments that did manage to form. Normally, the ratio of carbon-13 to carbon-12 in seawater is kept in a certain balance by life. But during a snowball event, that balance is completely disrupted, leading to a dramatic negative excursion in the ratio, which is precisely what geologists find in rocks from that time. Then, in the cap carbonates deposited during the thaw, we see a massive positive excursion as the ocean draws down the enormous burden of CO2. These chemical signals are the smoking gun, the indelible proof of a biosphere in total collapse and then recovery. The story of Snowball Earth is the ultimate testament to planetary resilience and the profound interconnectedness of Earth systems. It shows how the slow, rhythmic drift of planets can potentially provide the initial nudge that tips the world into ice, and how the planet's own volcanic heartbeat provides the means of its salvation, with the entire saga encrypted in the contrasting layers of jagged glacial stone and smooth, deposited carbonate. While the surface of our planet records the climate shifts driven by orbital cycles, the most profound and powerful geological forces originate from deep within, from the fiery, churning engine of the mantle. Rising from the very boundary of Earth's core, thousands of kilometers down, are immense columns of superheated rock known as mantle plumes. These are not gentle updrafts, they are thermal tornadoes, blisteringly hot and buoyant, that drill their way up through the solid but malleable mantle until they erupt onto the surface in spectacular fashion, creating some of the most dramatic volcanic features on the planet. We see their handiwork in the isolated island chains like Hawaii and the immense outpourings of lava that form large igneous provinces, such as the Deccan Traps in India or the Siberian Traps in Russia. For a long time, these events were viewed as purely internal affairs, random burps from a restless interior. But a fascinating and controversial idea is gaining traction, that the timing and intensity of these deep-seated eruptions might themselves be subtly orchestrated by the gravitational rhythms of our celestial neighbors, linking the very heart of our planet to the dance of the spheres. The mechanism for this incredible connection is the same gentle force that raises our ocean tides, gravity. We are all familiar with the moon's pull lifting the oceans, but that same gravitational attraction also flexes the solid Earth itself, a phenomenon known as Earth tides. The entire planet, from its crust to its core, bulges and contracts by a matter of centimeters in response to the tidal tugs of the moon and sun. While this seems insignificant compared to the vast scale of the mantle, it represents a constant, rhythmic source of stress. Now imagine a massive mantle plume, a vast column of hot, partially molten rock, slowly ascending from the core mantle boundary. It's a system under immense pressure, a colossal bubble of pent-up energy seeking release. The periodic stress from Earth tides, though small, could act as a trigger mechanism. It's akin to the tiny vibration that starts an avalanche. During a period of particularly high tidal stress, that extra nudge could be enough to fracture overlying rock, destabilize a magma chamber, or facilitate the final ascent of a plume head, ultimately leading to a massive volcanic eruption. This means the alignment of the moon and sun, and even the slower, grander gravitational influences of other planets could potentially provide the final straw that breaks the geological camel's back, unleashing the fires from below. The evidence for this is not found in a single smoking gun, but in the patterns hidden within the volcanic rocks themselves. When we look at the largest volcanic events in Earth's history, their timing is anything but random. The eruptions that created the Siberian traps, which coincided with the Permian-Triassic extinction, and the Deccan traps, which erupted alongside the dinosaur-killing Chicxulub impact, didn't happen in isolation. Intriguingly, when scientists use advanced radioactive dating techniques on the layers of lava in these massive formations, they often find that the eruptions occurred in pulses. It wasn't one continuous flow, but a series of gigantic bursts separated by periods of relative quiet. When researchers analyze the timing of these pulses, they sometimes find a startling correlation with known astronomical cycles, particularly the 400,000-year eccentricity cycle governed by Jupiter's gravity. It suggests that the deep Earth might be responding to the same celestial metronome that paces our climate, with the mantle's most violent outbursts timed to the slow, gravitational music of the solar system. Further clues are locked in the geochemical fingerprints of the lava. As a mantle plume rises, it can melt different parts of the mantle, and the chemical signature of that melt, the ratios of specific isotopes of elements like strontium, neodymium, and lead changes depending on the depth and composition of the source rock. In the layered stacks of lava that make up the Deccan traps, geologists have detected a clear and abrupt shift in these isotopic ratios partway through the eruptive sequence. This indicates that the source of the magma changed dramatically during the event. One compelling explanation is that the initial shock of the Chicxulub impact, itself a product of planetary drift perturbing an asteroid's orbit, sent seismic waves reverberating through the entire planet, potentially disrupting the plume's ascent and stirring the mantle to tap into a different, chemically distinct reservoir of rock. The rocks themselves are telling a story of a deep Earth system that is far more sensitive to external forcing than we ever imagined, where events happening millions of miles away can leave a permanent chemical signature in the very bedrock of our world. This paradigm shift forces us to see our planet as a completely integrated system, where the line between the celestial and the subterranean becomes beautifully blurred. The concept of planetary drift is no longer just about orbits and climate. It extends all the way down to the core mantle boundary, suggesting that the gravitational influences of the Moon, the Sun, and the other planets are not merely surface-level phenomena. They are a constant, rhythmic pressure that resonates through our entire world, capable of modulating the most powerful forces we know. The next time you see a map of the Hawaiian Emperor Seamount chain, with its elegant curve tracing the movement of the Pacific Plate over a stationary hotspot, consider that the pulsing heart of that hotspot might itself be beating in time with a rhythm set by the cosmos. It reveals a reality where the deepest geological processes are part of a grand, interconnected cosmic dance, and the evidence is forever frozen in the vast volcanic monuments that dot our planet's surface. We are now living in a new geological moment, an era defined not by asteroids or ice ages, but by us. Scientists call this proposed new chapter the Anthropocene, the age of humans, a time when our species has become the dominant force shaping the planet's geology and ecosystems. From the concrete of our cities to the plastics in our oceans, we are depositing a global layer of material that will be unmistakable in the rock record millions of years from now. This human signature intersects with a much older, slower process, the relentless and unchanging drift of the planets. While our actions are causing rapid, dramatic change on a scale of decades, the celestial mechanics of our solar system continue their stately, multi-thousand-year dance, a rhythm that will influence Earth's climate long after our cities have turned to dust. The profound lesson from reading the ancient rock archives is that these two timelines are now in conversation. Our short-term decisions are being imposed upon a planet whose long-term fate is still guided by the gravitational pull of the Sun, Moon, and other planets. Understanding this deep time context is not just academic, it is crucial for navigating our future. The Milankovic cycles that pace the comings and goings of ice ages for millions of years have not stopped. We are currently in an interglacial warm period within a larger ice age cycle, and left to its own devices, the Earth would eventually, over tens of thousands of years, cycle back into a glacial period. The orbital parameters are still shifting, gently altering the distribution of sunlight across the globe. However, humanity has thrown a massive wrench into this natural machinery. By releasing vast quantities of greenhouse gases from burning fossil fuels, we have artificially warmed the planet at a rate that dwarfs the slow, astronomical forcing. This creates a complex and dangerous interference pattern. We are effectively suppressing the natural descent into the next ice age, but we are doing so with a chaotic and unpredictable heating effect that could destabilize the entire climate system the Milankovic cycles once so rhythmically governed. This is where the wisdom stored in ancient rocks becomes our most vital guide. Those layered sedimentary formations, those isotopic signatures from past warm periods, are not just a history book, they are a library of experiments run by planet Earth itself. They show us how the climate system responded to different levels of greenhouse gases when the orbital configuration was similar to what it will be in the coming millennia. By studying the PETM, the Paleocene-Eocene thermal maximum of 56 million years ago, we can see what happens when a large pulse of carbon enters the atmosphere and oceans over a short geological time span. The rocks from that era record massive shifts in ocean chemistry, extinctions in the deep sea, and migrations of species on land, a preview of the potential consequences of our own actions. These ancient analogues provide the only tested data we have for how a planet with our specific orbital parameters and continental configuration responds to extreme warming, allowing us to refine our climate models and improve predictions about sea level rise, ocean acidification, and ecosystem collapse. In this way, the story encoded in stone transforms from a fascinating mystery into a practical tool for survival. It teaches us humility, reminding us that we are recent arrivals on a planet with a 4.5 billion year history of profound change, most of it directed by forces far beyond our control. Yet it also grants us a unique responsibility and a form of awareness no other species has possessed. We can read the past and, in doing so, foresee the long-term consequences of our present. Every ton of concrete we pour, every layer of plastic we bury, and every part per million of carbon dioxide we add to the atmosphere is becoming part of the stratigraphic record. We are, quite literally, writing our chapter into the cosmic story written in stone. The question the rocks will answer for future geologists is what that chapter will say. Will it be a brief, catastrophic spike of a civilization that failed to understand its place in deep time? Or will it be a testament to a species that learned to read the celestial rhythms of its home and chose to harmonize with them, ensuring its story continued for millennia to come? For centuries, the stories locked within Earth's rocks were like a library written in a language we could only partially decipher. We could read the broad strokes, the volcanic eruptions, the ancient seas, the mountain-building events, but the subtle, cosmic whispers encoded within the stone remain just beyond our grasp. That is, until now, a technological revolution is fundamentally transforming the field of geology. granting us a powerful new set of tools to finally translate the most intricate details of the planetary drift narrative. We are no longer just looking at rocks, we are reading them with a clarity and precision that would have been unimaginable just a few decades ago, turning the entire Earth's crust into a high-resolution chronicle of our solar system's dynamic history. At the heart of this revolution is our newfound ability to measure the unbelievably small. High-resolution mass spectrometry, for instance, allows scientists to perform what can only be described as geological microsurgery. Imagine a single tiny zircon crystal, smaller than a grain of sand, that has survived for over 4 billion years. Inside that crystal are minuscule amounts of uranium and lead atoms. As uranium radioactively decays into lead at a known, constant rate, it acts like a perfect stopwatch. Modern mass spectrometers can now measure the ratio of these two elements with such incredible accuracy that they can date the formation of that zircon crystal to within a few 100,000 years, a blink of an eye on a planetary timescale. This precise dating is the bedrock upon which we can build a reliable timeline, allowing us to say with confidence that a specific layer of volcanic ash in Morocco was deposited at the exact same moment as a layer of sedimentary rock in Canada, enabling us to correlate events across the globe and see the synchronous effects of a shared celestial trigger. But the secrets go even deeper than age. To understand the environment in which a rock formed, we need to analyze its chemical composition at a microscopic level. This is where synchrotron light sources come in. These are massive, donut-shaped particle accelerators that generate beams of light billions of times brighter than the sun. By focusing this intense light onto a microscopic spot on a rock sample, scientists can essentially tease apart its atomic structure. They can map the distribution of specific elements and even different isotopes within a single fossil shell or a layer of clay. For example, they can scan across the growth rings of a 200-million-year-old clam shell and see the seasonal variations in ocean temperature recorded by the shifting ratios of oxygen isotopes, effectively reading the weather report from the time of the dinosaurs. This allows us to reconstruct past climates with astonishing detail, directly observing the climatic consequences of those Milankovic cycles that were themselves driven by planetary gravitational pulls. While these lab-based techniques give us intense detail on a microscopic scale, another set of advancements allows us to see the grand continental scale patterns. Satellite imaging and remote sensing technology have given geologists a god's-eye view of the planet. Instruments like those on NAS, a Landsat or ESA's Sentinel satellites can detect subtle variations in mineral composition, rock moisture, and even magnetic fields from hundreds of miles in orbit. This is invaluable for spotting the large-scale geological structures that are the hallmark of planetary-scale forces. A geologist on the ground might see only a single, twisted layer of rock in a mountainside. But from space, that same layer can be traced uninterrupted for hundreds of miles, revealing it as part of a massive fold thrust up by the collision of tectonic plates, a collision that may have been influenced by long-term changes in tidal stress. Satellite radar can even measure the slow, millimeter-scale uplift of a continent over years, providing real-time data on the ongoing tectonic processes that are the modern expression of this deep-time planetary dance. The true power of this technological leap is realized when we combine all these tools. We can use satellite data to identify a promising rock formation that shows large-scale rhythmic layering. We can then go into the field and collect samples, using mass spectrometry to precisely date the start and end of that deposition. Finally, we can bring thin slices of the rock to a synchrotron to analyze the geochemical variations within each individual layer, confirming they match the predicted patterns of an orbital cycle. This multi-pronged approach turns a hypothesis into a verified fact. It allows scientists to rigorously test complex models of planetary migration by searching for their predicted fingerprints in the rock record. For instance, a model might suggest that a specific resonance between Mars and Earth occurred 50 million years ago, causing a 2.4 million-year climate pulse. We can now go to rocks from that exact time period, analyze them with these tools, and either find that pulse or rule it out. This transforms geology from a descriptive science into a predictive, experimental one, where the rocks themselves become the laboratory for testing our understanding of celestial mechanics. We are no longer just passive observers of the past. We are active detectives, using the most advanced tools at our disposal to interrogate the evidence and piece together the full, magnificent story of our wandering solar system. While the connections we've drawn between celestial mechanics and terrestrial geology are compelling, it's crucial to step into the world of scientific debate, where these ideas are rigorously challenged and refined. Not every geologist is convinced that the subtle gravitational tugs of distant planets leave an indelible mark on our rocks, and their skepticism forms a vital part of the scientific process. The core of the controversy lies in a fundamental question: how can we be sure that a pattern we see in the geological record was truly caused by planetary drift, and not by Earth's own powerful and unpredictable internal processes? Our planet is a dynamic, seething system of its own, with a molten core generating a magnetic field, a convecting mantle driving plate tectonics, and a crust constantly being recycled. These internal forces are so immense that many scientists argue they easily drown out any faint celestial signal. Consider the case of the Deccan Traps, the massive volcanic province in India that erupted around the same time the dinosaurs vanished. While some researchers point to evidence of orbital forcing or even an impact-triggered amplification, others maintain that this colossal igneous event was primarily driven by a massive mantle plume rising from the deep Earth, a purely internal phenomenon that just happened to coincide with an asteroid impact. The coincidence in timing, they argue, is just that, a coincidence. The Earth has experienced many large igneous provinces throughout its history, and not all of them align neatly with impact events or specific orbital configurations. This school of thought emphasizes the parsimony of Occam's razor. The simplest explanation, one that doesn't require invoking external celestial triggers, is often the most likely. They posit that the complex, chaotic systems within our planet are more than sufficient to explain its geological history without needing to look for causes millions of miles away. The debate gets even more nuanced when we examine the statistical methods used to find these patterns. Cyclistratigraphy, the science of reading orbital cycles in sedimentary layers, relies heavily on advanced mathematical techniques like spectral analysis to find repeating signals in the noise of the rock record. Critics rightly point out that any long, complex dataset is likely to contain some seemingly regular patterns purely by chance. It's a phenomenon known as the red noise problem, where natural, random variations can mimic periodic signals. Isolating a true astronomical signal requires not just finding a rhythm, but demonstrating that its specific periods match the known Milankovic cycles, and that these rhythms are consistent across vastly different rock types and locations around the globe. A rhythm found in Italian limestone must also be present in deep sea cores from the Pacific and in terrestrial coal deposits from North America to be considered a true global signal. This is a very high bar to clear, and for many proposed correlations, the evidence isn't yet robust enough to convince the entire scientific community. Furthermore, the Earth system is riddled with its own internal feedback loops that can create cycles independent of any astronomical forcing. The carbon cycle, for instance, has its own rhythms of storage and release. A volcano erupts, releasing CO2 and warming the planet, which accelerates weathering of rocks, which pulls CO2 back out of the atmosphere, leading to cooling. This could theoretically create a periodic climate signal all on its own, without any need for a change in planetary orbits. The challenge for proponents of planetary geological links is to untangle these internal cycles from external ones, to prove that the driver came from beyond our world. This often requires incredibly precise dating to demonstrate that the geological event happened first, followed by the climate response, in a sequence that only makes sense if the initial trigger was a change in sunlight caused by an orbital shift. Yet, despite these valid criticisms, the field is far from stagnant. This healthy debate is the engine of scientific progress, driving researchers to develop ever more sophisticated tools to test their hypotheses. The way forward is not through less research, but through more precise and interconnected data. The key to resolving these controversies lies in improving the resolution of our geological timelines. With techniques like uranium lead dating now able to pinpoint the age of volcanic ash layers with uncertainties of less than 50,000 years, we are finally approaching the level of precision needed to definitively match geological events to specific orbital configurations. Additionally, the rise of big data and machine learning allows scientists to analyze vast geological datasets from around the world simultaneously, searching for globally synchronous patterns that would be impossible to explain by local internal processes alone. The ongoing debate doesn't weaken the fascinating idea of planetary drift being recorded in rock. It strengthens it. This rigorous, often contentious back and forth is what separates a captivating speculation from an established scientific theory. It forces researchers to be more careful, their models more robust, and their evidence more overwhelming. Every valid criticism raised forces a refinement of the methods and a tightening of the evidence. This process ensures that if and when a consensus is finally reached, it will be built upon an absolutely solid foundation of interlocking evidence from astronomy, geology, chemistry, and physics. The controversies remind us that the story of our planet is the most complex mystery we will ever attempt to solve, and that every new chapter we decipher in the stone must be read with both wonder and a healthy, rigorous skepticism. The most exciting developments in our quest to decipher the cosmic story in stone lie not in the past, but in the future, a future built on the powerful and necessary integration of two fields once considered distant cousins, astronomy and geology. For too long, these disciplines have operated in parallel, one gazing outward to the heavens, the other looking downward at the ground. But the evidence is now undeniable that their stories are one and the same. The future of understanding planetary drift hinges on tearing down these academic silos and building a new, unified science of planetary evolution, where astrophysicists and field geologists work side by side to read the solar system's complete biography. A huge leap forward will come from the sheer physical act of touching other worlds. Robotic missions are no longer just about taking pictures. They are about becoming interplanetary field geologists. NASA Perseverance rover is right now, as we speak, drilling into the sedimentary rocks of an ancient Martian river delta, carefully sealing those core samples in pristine tubes to be returned to Earth by a future mission. Imagine holding a piece of Martian mudstone in a lab, a rock that formed in a lake that dried up billions of years ago. Within its layers, we could find the same rhythmic bedding patterns we see on Earth, but tuned to the different orbital frequencies of Mars. Analyzing those rhythms would give us an entirely independent record of how the gravitational tug of the gas giants has influenced the inner solar system, a record free from Earth's constant tectonic recycling. Similarly, upcoming missions to the metal-rich asteroid Psyche or to the moons of Jupiter and Saturn will bring back samples from primordial building blocks that never formed planets. These pristine time capsules will provide a chemical baseline, allowing us to better distinguish between what is truly terrestrial in our rocks and what is an imported signature from extraterrestrial bombardments triggered by planetary migrations. But we can't just wait for samples to fall into our laps. We are also building digital twins of our solar system. The revolution in computational power is allowing scientists to run incredibly sophisticated N-body simulations, modeling the gravitational dance of every planet, moon, and major asteroid over billions of years. These aren't simple animations. They are complex physics engines that can now incorporate factors like the gravitational influence of the galactic tide and the subtle effects of general relativity. The goal is to run these simulations backwards, to rewind the solar system's tape and see which initial conditions and planetary migration paths best reproduce the current orbits we see today. The real magic happens when we then take the predicted timelines of chaos from these models, say, a specific date when Jupiter's migration should have scattered asteroids, and cross-reference them with the hard evidence in Earth's rock record. If the model predicts a bombardment at 4.1 billion years ago, we can then go to the oldest zircons from that time and look for the geochemical and physical shock evidence. This creates a powerful feedback loop. The rocks test the models, and the models tell the geologists exactly where and when to look in the geological record for the next clue. This grand synthesis will require a new generation of scientists who are truly bilingual, fluent in both the language of celestial mechanics and the language of mineralogy. We are already seeing the birth of these hybrids, the astrogeologist who can operate a mass spectrometer to date a rock and then write code to model its exposure to cosmic radiation, the climatologist who can analyze isotopic ratios in an ice core and also calculate the changes in solar insolation from a shift in Earth's obliquity. Major research institutions are now fostering these collaborations, creating centers where planetary scientists, geochemists, and astrophysicists can work in the same labs, literally looking over each other's shoulders to connect a microscopic feature in a thin section to a grand-scale orbital model. Their collective work will move us from simply observing correlations to finally understanding the mechanisms, revealing not just that planetary drift leaves a mark, but exactly how it does so, from the moment a gravitational resonance disturbs an asteroid's orbit to the moment the iridium from that impact is deposited as a thin, global layer in clay. This is the thrilling path ahead, a journey that promises to fully unite the story above with the story below, revealing the complete and breathtaking history of our wandering solar system, all written in the pages of stone we have only just begun to learn how to read. From the humblest sedimentary layer to the most rugged metamorphic outcrop, Earth's rocks are silent witnesses to the grand ballet of planetary drift. They hold encrypted records of orbital shifts, gravitational resonances, and cosmic events that have shaped our world over billions of years. Think about that for a moment. The very ground we walk on, the cliffs we admire, the stones we skip across a pond, each is more than just a piece of our planet. They are pages in a cosmic diary, written in a language of chemistry, magnetism, and rhythm, patiently waiting for us to learn how to read them. This isn't just about understanding the past, it's about preparing for the future. By deciphering these ancient archives, we gain something priceless: context. We see that our world is not a static stage but a dynamic participant in an ever-changing solar system. The same gravitational forces that paced the ice ages, triggered volcanic upheavals, and guided asteroids will continue to influence Earth's long-term climate and geological destiny. Our current period of rapid, human-driven change is just a brief moment superimposed upon these much grander celestial cycles. The rocks teach us humility, showing us that we are part of a system far larger and older than ourselves, but they also grant us a unique form of power, the power of foresight, allowing us to use the deep past as a guide for the challenges ahead. And the most exciting part, this story is still being written. Every new technological advance, every sample returned from another world, every sophisticated computer model brings us closer to a truly unified theory of our solar system's evolution. The dialogue between the geologist with a rock hammer and the astrophysicist with a telescope is growing into a continuous conversation, revealing connections we are only beginning to imagine. This journey of discovery reminds us that curiosity is our most valuable tool, and that every stone, no matter how ordinary it seems, has a tale to tell about our place in a harmonious, interconnected universe. Thank you for joining this exploration into the deepest of times. If you've enjoyed unraveling these mysteries with us, please like this video, subscribe to the channel, and share your own thoughts and questions in the comments below. We love hearing